A fantastic example of variable forces occurs in springs, and springs also are nice examples of changing energy types. We've talked about kinetic energy, we've talked about gravitational potential energy, and we can also talk about elastic potential energy. At the moment, the springs are hanging in a particular way. We could also have an example of a spring along a horizontal surface, and we'll look at some of those later. We are assuming that these springs have no mass. That is a little bit of an assumption, but often the forces and masses that we're dealing with are large enough that's a fair enough assumption. There are some limitations to this simulation I just want to show you. If I were to stretch this spring out and I were to release it, it actually double in on itself. So look, it's not a perfect simulation, but it's pretty nice for the purposes of what we're doing here. So I want to apply a force to this spring. So this is the spring as it normally would be, and this is the spring when it eventually slows down to a stop. At the moment, there's a force due to gravity is what's pulling this spring down. And we can apply additional force if I wanted to drag this mass downwards. Let's get rid of that gravity force. So if I'd have that force due to gravity plus an additional force pulling it down, I'd be applying, a larger force to it here. So stop it again. The spring is applying a force in response to that. So if I drag it down here, the spring is applying a much larger force here than when I first set it up and just hung the mass and didn't apply my own force here. Similarly, if I were to push that spring, so notice when it's the same size as the unstretched spring, there's no force the spring's exerting here because it's happy, it's at its equilibrium position. But if I were to shove that mass further upwards, the spring is again trying to get back to its natural or its unstretched length. So we can very clearly see, and you've probably felt this playing with springs before, that the amount of force that a spring exerts is variable. Not only does it vary in magnitude, we can see much larger here, 0 here, but it also varies in its direction. So that's a good example of variable force. We can see that this spring is always going to be exerting a force in the opposite direction to the displacement, and we measure displacement from this equilibrium line here. So if we pull that spring down, the force exerted is up. If we push that spring up, the force exerted is down. So that's why in Hooke's law that we're going to be talking about a little bit later, there's a negative sign in there. It's just indicating that the force that the spring is exerting is the opposite direction to the displacement. And again, we're using this 0 line to be the equilibrium position of the spring. That's where it's at its natural or its unstretched length, when it's just chilling out. Again, we're assuming it has no mass. So this is a massless spring. It's not being pulled down by gravity yet. So I've placed the spring in a particular position here, and for the calculations that we're going to be doing, for example, if I wanted to calculate the size of that force, there's 2 things that I would need. Number 1, I'd need to know the value of the spring constant. That's a measure of how stiff the spring is, basically, how strongly it's able to pull back or push back on an applied force. And number 2, I need to know the stretched length. That stretched length is not the length of the spring itself, but we care about how much longer it has become. We do not care, again, about the total length that we've got of this spring. We merely care about how much it has changed from its original length. So in this situation, if we put our ruler up here, it'd be a smidge over 55 centimeters. If I were to move the spring up here, we are now measuring to this point here. We only care about what the difference in length is. We don't care whether it's positive or negative. We just care how much shorter or longer is this buddy. There are 2 things that we can use to figure out that force, and that is Hooke's law. So in what we've got here, this is our unstretched length of spring. If the spring were compressed, that's the word here, to compress is to squish it up, this would be the change in length, and we call that change in length delta x. And you would have noticed delta x in our spring potential energy formula previously discussed. In this example, if we've stretched out the spring, and maybe we'll label this as delta x1, and then this one here, this is delta x2. They're 2 different amounts. I haven't made them the same. So I said that we needed to calculate the force, we needed to know 2 things. we needed to know the spring constant, and that's K. Sometimes known as the stiffness coefficient, but I'll be referring to it as spring constant. That has units of newtons per meter, not Newton meters like impulse, newtons per meter. We also needed to know the stretched length. Again, I don't care about that total length here. It means nothing to me at all. All I care about is the stretched or the compressed length, the change in length. So delta x equals change in spring length from unstretched length. I also referred to this as the equilibrium position. That's when it's just hanging out and not doing anything, and the net force upon it is 0. Now, I did mention that the force, this is the force the spring exerts. So technically, we need a negative sign here because the force that the spring exerted was in the opposite direction to the displacement. We will be, like some of the equations that we've done, ignoring this negative sign for our calculations. It's merely indicating a direction. So you might have seen in the simulation before that the force was proportional to the amount that it was either stretched or compressed. And proportional means that it's linear and it goes through 0. Now you might do a prac with this and not necessarily get your points going through the origin here. That would indicate some sort of systematic error. But theoretically it should do. So we've got the force on the spring on this axis. I think I should have mentioned this should be in meters, and force by now you should know is in newtons. We've now got the extension of the spring. Delta x is plotted on this axis here. So like I mentioned, there are 3 ways we can refer to this: elastic strain or spring potential energy. It's energy stored in a material that has been stretched or compressed from its normal shape. Now, one thing I did mean to mention with our spring, it's not really on the course, but there is a point where you can break this. If you applied too much of a force this way, your spring would get kind of stretched out and stuck and it wouldn't be able to go back to this length here. That's called stretching the spring beyond its elastic limit, and that's not what Hooke's law covers. It's talking about when you don't break your spring effectively. So we said in the past, if we had a force displacement or force distance graph, something like that, the area underneath would tell us about the work done. So we're going to use the graph that we have just come up with. Notice we're just using F equals K delta X. We're not looking at that negative sign like I previously warned you about. And we're going to talk about the area under this graph. And remember, it's the work done. So area under the graph, if we were interested in this area here, we only need to do this derivation once. I just want to show you where the formula we're about to come up with came from. So how would we do that? Well, it's a half base times height. So a half, the base is going to be delta x, and the height, we're going to call it this particular value f. I know it's not perfectly lined up, deal with it. So we said though, times the force was equal to K delta X. So let's replace that with the force here. So K delta X. So that means the work done, which is the energy stored in the spring, I'm going to use E subscript S for spring potential energy. That's equal to a half. Let's put the K next. And we've got delta X all squared. For some reason, I just find it useful to put the delta X in brackets. So this is how you find spring potential energy. So we've effectively learnt 2 new formulae here. We've learned Hooke's law deals with the forces that are acting, whereas the spring potential energy equation deals with the energy. You need to be cognizant of whether you need to apply an energy approach or a force approach, because they're 2 very different quantities. So let's look at the first example we've got here. Find the extension. So that's going to be delta x. Remember, delta x could be an extension or a compression. When a stretching force of 30 newtons is applied to an extendable spring of stiffness 75 newtons per meter. We've got delta x, we've got F, and, we care about delta x, we've got F, and we've got K, so we need to use F equals K delta X, also known as Hooke's law. We care about delta X, so it's going to be F divided. So we get 0.40 meters to 2 sig figs. We're now asked to find the spring constant of a spring which requires a force of 200 newtons to compress it by not 40 centimeters, but 0.40 meters. Oh, that's interesting. It's the same number as before. I think that was not intentional. Have a go at this one, see if you get the same result. If this is the first time you're watching this video, you wouldn't have seen that I made an error before. I actually put in the 40 centimeters rather than the 0.4 meters for the extension here. As you can see, the units of K are newtons per meter, so we definitely need that in meters, not centimeters. I even converted it. Don't know what I was doing, but here it is. It's correct now. 1.5 kilo mass is suspended from a spring with a stiffness coefficient of 45 newtons per meter. How far does it stretch the spring? Looks like we're using Hooke's law again. Now with this one, we're not directly told a force, but if we have a spring with a mass attached to it, the only force acting will be the force due to gravity acting on that mass, which we know is mg. Okay, let's look at this next one. We've got a horizontal pinball machine. So we're not going to have, like our vertical spring system before, we're not going to have a mass with mg acting on it. We're going to have some other force acting. It looks like with the spring ball machine, we're going to have someone pulling that pin outwards to be able to, I think I said pinball machine, pulling that plunger out to be able to start playing the game. So we've got 1 kilogram ball. It's at rest against a plunger. Now, the mass of this plunger doesn't matter for what we're about to do. We're told the spring constant, so this means the newtons per meter means for each meter the spring is pulled out, it can apply 250 newtons. Now, like I mentioned, we're probably not going to be compressing or extending this particular spring by a meter. That would be larger than the pinball machine itself. But it is nice to know what that value represents. So, much smaller distance here. What force must the player exert on the plunger to compress it by this amount? That's delta x. Okay, I get 10 newtons for this one. Not a huge amount of force here. In compressing the spring, how much work has been done? So, you cannot use work equals Fs for this. That is not okay. Because the amount of force that the spring itself is exerting upon that person's hand is changing. So, that's a variable force, so we need a different approach to that. So luckily, we know that work causes a change in energy. This spring, if it started off at its natural or unstretched, uncompressed length, then it had no spring potential energy. But if it was then stretched, it has spring potential energy. So finally it has spring potential energy and initially it had 0. That means the change in energy has got to equal that final spring potential energy. Now, we know spring potential energy is equal to a half K delta X all squared. So, let's calculate that. K was 250. So I get 0.2 joules. Notice, if we did this force, 10 newtons, times this value here, we would have gotten double the actual amount of work done. It is a variable amount of force. The person's pulling this way, so the spring is applying a force this way. As this force gets larger, the spring force gets larger. So we cannot use work equals Fs because we have a variable force, and that's the kind of thing I'd be putting on my note sheet. It says, when the player releases the handle, with what velocity will the ball leave the plunger? We have got an excellent example of energy conversions happening here. In this example, spring potential energy, so work was done to extend the spring. Now that that spring has spring potential energy and it's stationary, we're about to release it. And that means that spring potential energy is going to get wholly converted to kinetic energy. There's no gravitational potential energy here because we're dealing with an entirely horizontal surface. We're not changing our height. So we've got spring potential energy going to kinetic energy. So given that we know what the spring potential energy is, we're going to be applying this value in this question here. So why is that so helpful? If we want the velocity, knowing the kinetic energy will unlock that, and that's why we needed the mass of the ball previously. Again, we don't need the mass of the plunger, not relevant to what we're doing here. Might have been relevant in another example that I've cut off. You've got two choices here. You could substitute in the value, knowing that all the spring potential energy was converted to kinetic. You could put in 0.20 here and then solve for V. I want to do algebra first. we're going to just take the positive of the velocity here. Okay, I really like that this cancelled out, so we got square root of 4 and 2 sig figs, 2.0 meters per second. Alrighty, this one we're given a graph, and we've got a horizontal spring again. So a spring behaves as depicted in the graph below. We've got the force on this axis here, and we've got the compression on this axis. Check those units, newtons, meters, great. One important thing to know is that the gradient of a force distance graph tells you what K is. So K is gradient of force, and I'm going to put delta X graph. This is an old question, so they've labelled it as X, but we know we're talking about delta X, a change in length here. We're probably going to need to find the value of K at some point, so should we do it now or should we do it later? Might as well do it now. So K is going to be the gradient. Let's choose a point. You could do rise over run or y2 minus y1 on x2 minus x1. So we've got that for later. Again, if there was a question that asked for it, we'd come up to it. So we're told that is how this spring here is going to behave. It tells us for what compression, what force it's going to exert, basically. And again, it's a variable force. Body of mass 0.5 kilos is traveling at this speed. It approaches a spring which is fixed to the wall as shown before. Friction can be neglected. Thank you. Body comes to rest instantaneously at time t1. And the spring is compressed by a total amount of x1. So this is delta x. They've called x1. Kind of annoying, but that's what the question's told us. It then rebounds. So in this scenario, we've got an object that is moving, having kinetic energy, no spring potential because it hasn't reached the spring yet in the system, no gravitational, we're not at a height. Eventually, the spring will be all squished up and the mass will be stationary. So all of that kinetic energy is being converted to spring potential energy here. Okay. So it asks us to find the value of x1. That's the amount that the spring is compressed by. Now remember, we've got all of those different things in our toolkit. We could attempt suvat, but we've got an initial and final velocity, but we don't have an acceleration. And we can't actually use suvat because it's going to be a variable force. It will be a variable acceleration. So can't use suvat, can't use a force approach because the force is changing. So let's use an energy approach. We're going to use the fact that kinetic energy is transferred to spring potential energy. The spring potential energy is all converted to kinetic, so we can say that the size of the spring potential energy is got to equal the size of the kinetic energy. So that means a half K delta X all squared has got to equal a half mv squared. And we're talking about this value of V here. Okay, you know how I feel about having halves everywhere. Let's get rid of those. And let's rearrange this one for delta x. Let's replace delta x, though, with x1. So I'll put that in the next line. K x1 squared equals mv squared. We've got to use what they've provided in the question. Okay, to find x1, we need to divide k over the other side. And we need to take the square root. We just care about the size here. The mass is in reference to this block here because this is the thing that had kinetic energy. 0.5. The velocity of that box is here. And K we previously had calculated to be 200. We squaring it? No. X1, 0.10 meters. Nice. Okay, next question. Which of the graphs best represents the kinetic energy of the body as a function of the compression x1 of the spring? This is a tricky question. Doesn't mean that it couldn't be on the exam. Let's talk about what the answer isn't. So, number one, the kinetic energy has got to be changing. So we're not going to have a constant kinetic energy here. Let's go back to that example for a moment. Sorry, I meant simulation, not example. Let's just clean this up a little bit. I will acknowledge that we're looking at a vertical scenario here rather than a horizontal, as in our current example, but it still provides us with some useful things to discuss. So, the kinetic energy is very much variable. You notice for an instant here and an instant here. The object rests for just a nanosecond. So the kinetic energy is 0 at the top and bottom here. That's not relevant to the question we're doing here. I'm just talking generally about springs, because we've got the situation where we're going to have a mass colliding with the spring and squishing it. So we're going to really have from like here. No, here. Yeah. Anyway, the kinetic energy is very much variable. At the top of the spring and at the bottom of the spring's motion, it was 0 because it stopped momentarily. And it turns out right in the middle of its motion, I'll talk more specifically about this at another time, the kinetic energy is a maximum. And yeah, let's keep going with the actual example. So like I said, we can't have this one be it because it's saying the kinetic energy is constant. It's kind of annoying. It's got this line down here, but whatever, just ignore it. This would be a correct graph if it was the total energy though. The total energy, the kinetic energy plus, in this example, we've just got a horizontal spring, so there's no gravitational potential energy. So in this example, the total energy, let's do E subscript total, equals the kinetic energy plus the spring potential energy. No gravitational potential energy because we've got a horizontal spring system here. Ooh, that was a good drawing. So it's just traveling like this, not changing in height. So the total energy will be constant. Unfortunately, I don't know right off the top of my head how the kinetic energy relates to the compression of the spring, but I do know how the spring potential energy relates to the compression of the spring, because E spring equals 1/2 K delta X squared. So that means the spring potential energy, we can ignore the constants for what we're about to talk about. The half doesn't change and the K doesn't change, but the spring potential energy is proportional to delta X all squared. So that's saying whatever change happens to X, square it, and that's the change that happens to the spring. Now you might recall in mathematics, if you had a quadratic, y is proportional to x squared. Anytime you have something proportional to something squared, in this particular circumstance, it means that we're looking at something parabolic. Let's look at the situation that we had again. Originally, the spring as it is at its natural length. So the spring potential energy would start off at 0. Let's draw spring potential energy in pink. The spring potential energy is proportional to x squared. So that means we've got to have a quadratic happening here. And it's going to be like, whoop. If the value of x doubles, so just saying going from this point to this point, the value of TE doesn't just double, it quadruples. So we've got to have that increasing gradient here. Okay, why is that helpful to know? Whatever this graph we have here, plus the kinetic energy graph, needs to give us our total graph here. So we need to think, okay, either A, B, or C, if we take the heights of that graph and add it to what we've currently got for the spring potential energy, it needs to give us a flat line. Now, if we were to add the straight line graph here, it wouldn't work. So let's draw in this one here. If we were to add this height and this height, that would be fine, but this height and this height would give us a weird dip. This height and this height would be this. So the total energy, I was just thinking about adding the heights at this point, these two heights and these two heights, we get a weird dippy graph here. That doesn't work. Oh, let's choose another color, eh? Green. Weird dippy graph, doesn't work. If we were to add the graph that we have, what color was I using? Pink. With this graph here, this would be an even dippier graph. If we're adding these two heights, 0 plus this gives us this point, this height plus this height gives us, well, it should technically be here, it's even worse, and this height plus this height gives us this. So, it definitely needs to be B. It needs to be B. I like to imagine it if I took this graph here and flipped it to add the heights. So I can like flip that over the x-axis. It's like it fits snugly into this line here. I can talk more about this in person. It's kind of hard when I'm waving my arms at a screen.